January 22, 2018, the Pryor Trust gas well in Pittsburgh County, Oklahoma. The well was operated by Red Mountain Operating, LLC, which contracted the Patterson-UTI Drilling Company to drill the well. In order to change a drill bit, crew members removed the drill pipe from the well. Approximately 3.5 hours later, a blowout and rig fire occurred, killing 5 workers.
Industry best practices recommend having 2 protective barriers in place at all times during drilling operations. But our investigation into the incident at the Pryor Trust well found that both of those barriers failed. The safety management system utilized at the well was simply not effective, and the result was a catastrophic blowout and fire.
The Pryor Trust gas well was comprised of vertical and horizontal sections being drilled to reach underground natural gas in the Woodford Geological Formation. During drilling, a diesel oil-based liquid called mud is pumped down through the drill pipe and back up through the area of the well outside of the drill pipe, called the annulus. When mud returns to the surface, it includes rock cuttings from the bottom of the well. Mud, however, has another important function. It is designed to add pressure to the well so that gas within the exposed geological formation is unable to enter the well during drilling. If that happens, and the gas is not detected, it can lead to a dangerous blowout. On January 21, 2018, Patterson crew members had been drilling the well for 10 days under the supervision of 2 contracted representatives from Red Mountain. They were drilling the horizontal section of the well. That morning, a crew member called a mud logger studied the rocks returning to the surface and found they were different than expected. He believed the drill pipe had inadvertently entered a different geological formation where Red Mountain did not intend to drill. Shortly after, gas started to escape from mud returning to the surface. The gas caused mud to spit out of equipment near the well and cover a portion of the rig. Around 11 a.m., the drilling crew adjusted piping so that mud returning from the well was routed to a piece of equipment called a mud gas separator that removed the gas from the mud. The separated gas was then routed to a flare to safely burn it. The size of the flare indicated that there was a significant amount of gas in the mud and that the well had likely become underbalanced, meaning that pressure from the mud was not keeping gas out of the well as intended. The crew continued drilling underbalanced until 3:30 p.m. when they stopped because the drill bit had become worn and needed to be replaced. The crew first circulated the well for 3 hours by pumping mud down the drill pipe and up the annulus. The flare continued while the well was circulating, an indication that the well remained underbalanced. While circulating, the Red Mountain representatives discussed how to remove the drill pipe from the well in order to replace the drill bit. The process to remove a drill pipe is called tripping. During any tripping operation, mud is pumped into the well to replace the volume of drill pipe being removed, which prevents gas from flowing into the well. In this case, the Red Mountain representatives decided to use a tripping method called calculated fill, which involved periodically pumping a calculated amount of mud into the well as the drill pipe was removed. They believed this method would keep the well contained if gas entered during the operation. But it was not a standard tripping method during normal drilling, so no one on the Patterson crew had performed it before, and they had no written procedure. The crew started removing the drill pipe at 6:47 p.m. The CSB found that while tripping the drill pipe from the horizontal section of the well, not enough mud was pumped and gas entered the well. The driller, who was controlling the operation from inside a building on the rig called the driller's cabin, did not see the discrepancy. That is because he had not been sufficiently trained on a new electronic version of a trip sheet, which is a form used to monitor and calculate whether a well is taking the proper amount of mud during tripping. As a result, he was unable to see that a significant amount of gas continued to enter or expand within the well, causing pressure in the well to increase and mud to backflow into a tank at the surface called the trip tank. In fact, pressure at the surface of the well had increased so much that the centrifugal pump the crew was using was no longer able to pump mud against the pressure of the well. Red Mountain's representatives decided to switch to higher pressure pumps, called mud pumps, to try to force mud into the well. They believed that the pressure applied by the new pumps would push any gas out of the well. But by the time the drill bit reached the top of the curve in the well, the CSB found that, unknown to drilling crew members, 20 barrels of gas had entered or expanded within the well. At that time, the drilling crew performed a 45-second flow check to see if gas was flowing in the well. The crew did not observe any flow of gas and believed the well to be stable, but the CSB determined that the flow check was inadequate. At 11 p.m., the drilling crew again circulated the well. While circulating, the rig's mud pits, which are tanks used to hold mud at the surface and are equipped with level sensors, gained 14 barrels of mud when they should have remained stable. This meant that the well gained approximately 14 barrels of gas, which caused the mud to escape at the surface. But the night shift driller had turned off the alarm system before the tripping operation, and no alarm sounded, so the large gain went unnoticed. Red Mountain's representatives then decided to pump a weighted volume of mud, called a pill, into the well, meant to generate enough pressure to prevent gas from entering the well. But a Patterson drilling crew member misheard Red Mountain's instructions over the radio, and they accidentally added lost circulation material to the pill. This material is designed to clog breaches in the well and is not intended to be in weighted pills. Although the mistake was discovered, the pill containing the lost circulation material was pumped down to the bottom of the drill pipe, clogging it. By 1:12 a.m. on January 22nd, the crew started to remove the drill pipe from the vertical section of the well, this time using the typical industry tripping method called continuous fill, where mud is pumped continuously into the well as the drill pipe is removed. But because the drill pipe was clogged, the mud was not freely draining into the well. The crew attempted to pump a weighted slug of mud into the drill pipe to push the clogged mud out, but this was not successful. With the drill pipe plugged, the drilling crew had to trip wet, meaning mud was in the pipe sections being removed at the surface. The drilling crew used what is known as a mud bucket to collect the mud from the drill pipe, which they drained into the trip tank. But the trip tank was also used to pump mud into the well during tripping. So the trip tank volume started to fluctuate as mud was pumped out to the well and drained in from the drill pipe. The fluctuations confused crew members, and they did not realize that while the drill pipe was removed from the vertical section, the well gained another 23 barrels of gas. When the bottom hole assembly, which is equipment at the end of the drill pipe that includes the drill bit, was near the top of the well, the crew finally removed the plugged part of the drill pipe. For the next hour, they tried to clear the clog. But at that time, and during a subsequent shift change, the well was still flowing, gaining another 31 barrels of gas and pushing more mud into the trip tank. No one saw the gain. At 6:10 a.m., the crew lifted the bottom hole assembly out of the well and closed the blind rams on the blowout preventer. They prepared a new bottom hole assembly for testing. When it was ready, a drilling crew member checked a pressure gauge on the rig floor to see if it showed pressure in the well, a safety precaution used before opening the blowout preventer. The pressure gauge showed no pressure. But at 7:57 a.m., when the blind rams were reopened so the new bottom hole assembly could be lowered into the well, 5 barrels of mud surged to the mud pits. At that time, a crew member pulled away the steel plate that had been covering the hole in the rig floor over the well. He waved over another worker who saw mud bubbling in the well, a sign that there was a significant amount of gas in the mud. That worker later told the CSB that he does not know if the mud bubbling was communicated to the driller. Between 7:57 a.m. and 8:35 a.m., while the drilling crew was testing the new bottom hole assembly, the mud pits gained another 102 barrels of mud, a very large volume. This significant gain likely displayed on the driller's data screen, but the day shift driller also chose to turn off the alarm system, and it is unknown if the driller saw this dangerous gain. At 8:35, with testing complete, the bottom hole assembly was removed from the well, and the mud pits gained another 12 barrels of mud, for a total influx of 207 barrels of gas into the well from the start of the tripping operation. A crew member saw mud flowing up out of the open blowout preventer stack. The mud was shooting up steadily, getting closer to the rig floor. The crew member told the driller, and the driller responded, that he was going to close the blind rams, but he never made it. Seconds later, mud blew upwards out of the well in what is known as a blowout. 2 workers on the rig floor ran into the driller's cabin, where 3 other workers were already located. The gas and mud then ignited, causing a massive fire. All 5 people in the driller's cabin were killed. The blowout continued for hours until a well control services company was able to shut in the well around 4 p.m. During its investigation, the CSB found data indicating that on the evening prior to the blowout, the night shift driller turned off the entire alarm system. Data also indicates that the day shift driller briefly turned on the alarm system, but then quickly turned it off again on the day of the incident. Other than that short period, the alarm system was off for 14 hours, leading to the blowout.
We were not able to conclusively determine why the drillers turned the alarm system off. A possible reason why they did is that the alarms were perceived as a nuisance or an annoyance. In fact, we found that had the alarm system been on, most of the alarms that would have activated during the 14 hours leading up to the incident likely would have been irrelevant to detecting the problems in the well.
For an alarm system to be effective, it must be configured so that the driller only receives alerts to conditions that require attention. But the CSB found that Patterson did not develop guidance to help drillers set the alarm system for the various operations performed on the rig, such as drilling, tripping, and circulating. Instead, to manage the alarm rate, both drillers apparently elected to simply turn off the alarm system.
We concluded that what's called a state-based alarm strategy is one way to solve this issue. For example, on a drilling rig, there could be different active alarms for each operation, such as drilling, tripping, and circulating, so that alarms critical to a certain operation do not become a nuisance when operating in a different state where those alarms are not needed.
Although there is a large body of guidance and recommendations on the design of alarm systems for hazardous operations, none are specifically targeted for the drilling industry. As a result, the CSB made a recommendation to the American Petroleum Institute to develop a standard on alarm management, specifically for the drilling industry, that addresses drilling's unique dynamic environment and provides guidance on implementing a state-based alarm system for different operating modes.
When the blowout started, 2 crew members on the rig floor ran inside the driller's cabin. 3 other crew members were already in the driller's cabin, and all 5 workers were killed.
It is unknown how long the victims remained alive inside the driller's cabin, but they had no viable escape routes. There were 2 exit doors from the driller's cabin, but both of those exit doors were blocked by flames after the gas and mud ignited. The CSB concluded that had the fire rating of the driller's cabin been ensured for a minimum time, with emergency escape options from the floor or from the back wall, there could have been a better chance for the workers inside to have survived this incident. Stan Christman is a drilling expert who consulted with the CSB on the prior trust investigation.
On a drilling rig, the operations are controlled from the driller's cabin by the key man, the driller. And he has a crew that works for him on the rig floor. The driller's cabin is located right next to the rig floor. He can see, talk over radio, even directly to the crew and get things done. Having the driller's cabin near the rig floor puts it closer to the hazards, and that is things happening on the floor, typically from the well. And these hazards are things that we could probably think further about. How do we improve the reliability and safety of these cabins for these unusual events?
Although there are best practices within the chemical industry for the location and design of control rooms, there is no guidance specific to drilling. As a result, the CSB made a recommendation to the American Petroleum Institute to develop guidance addressing the protection of onshore rig workers from fire and explosion hazards in the event of a blowout. The guidance will specifically address the design and location of the driller's cabin and establish minimum required evacuation methods from various locations on the rig. Flow checks are a safety-critical operation used to determine if gas or other formation fluids have entered a well, which could lead to a blowout. Patterson policies required flow checks to be performed at various times during the tripping operation. But the CSB found that of the 27 flow checks that were required by Patterson during the drilling of this well and the previous well, only 2 were performed, and those were inadequate.
There was a culture on this rig that accepted the non-performance of flow checks. Performing flow checks during the tripping operation, as required by Patterson, could have identified that the well was flowing and could have prevented the blowout.
The CSB found that the cause of the blowout and rig fire was the failure of both barriers that should have been in place during the operations leading to the blowout. Those 2 barriers were the primary prevention barrier, hydrostatic pressure produced by drilling mud, and the secondary mitigation barrier, human detection of gas entering the well and activation of the blowout preventer. When the well became underbalanced on January 21st, the primary protective barrier was lost, but work was not stopped so that the barrier could be reestablished by increasing the weight of mud, and no analysis on the loss of the barrier was performed.
We learned that Red Mountain had developed what they called a drilling prognosis, which is a type of well plan. But that plan did not specify what barriers were required or how to identify if a barrier was lost. And we found that development of a more comprehensive plan, such as what's known as the Well Construction Interface Document, which is used more widely in offshore drilling, was not required.
In fact, there are minimal federal regulations governing the safety of onshore oil and gas drilling operations. The Occupational Safety and Health Administration's Process Safety Management, or PSM standard, which would require a hazard analysis of the operation, does not apply to drilling. No other OSHA standard specifically covers drilling, and no other federal regulatory body oversees the safety of onshore drilling operations. With no federal safety standards for oil and gas drilling companies are governed by a patchwork of individual state laws. During its investigation, the CSB determined that the laws in Oklahoma, where the incident occurred, are not focused on safety, and instead stress maximizing production and eliminating the loss of hydrocarbons.
The CSB believes more focused and specialized regulatory coverage, like the OSHA PSM standard for the chemical industry, is needed to better control the hazards inherent to drilling. With the requirement for a more effective safety management system, drilling companies can avoid incidents in a proactive manner, protecting both their workers and the environment.
As a result, the CSB made recommendations to OSHA to either apply the PSM standard to drilling of oil and gas wells or develop a new standard with a safety management system framework similar to PSM that applies only to the drilling of onshore oil and gas wells. To prevent similar blowouts, drilling contractors and operators should develop a well construction interface document, bridging the operators and drilling contractors' safety systems and providing a barrier plan, including how to monitor barriers and how to respond if a barrier is compromised. Create procedures for operations, including tripping. Design alarm systems so that only the alarms indicating a condition needing drilling crew attention are active. regularly perform drills to test drilling crews' abilities to detect and respond to signs of influx, and implement an indicators program to monitor and improve policy implementation rates.
The blowout and massive fire at the Pryor Trust well was completely preventable. We hope our findings and recommendations are used by the drilling industry to promote safer operations so that similar tragic incidents can be prevented. Thank you for watching this CSB Safety video.